Hello everyone. In this video, we're going to go over the review for the Math 2023 Introduction to Probability and Statistics final. So we'll go over this question by question. These go in order of the notes, so you may want to stop and review the notes as you go through them. And then remember, there's also some additional problems posted so that you can get some additional practice outside of just what's on this review. Let's get right into it. So going all the way back to section 1-2, we learned about different ways to classify data, and we consider data that was either discrete or continuous. Remember that discrete data is data that is countable. So things that you could point to and say 1, 2, 3, 4, so on. Where continuous data can take on infinitely many values, and it's typically going to be something that is measured. So a shift manager records the number of Corvettes manufactured during each day of production. So this right here, we're looking at the number, so it's going to be discrete. If we were looking at how long it would take for a Corvette to be manufactured, maybe 5 hours, 23 minutes, 14 seconds. And again, we can always get more precise, hence the continuum. That would be the idea of a continuous data set. Now, if we were to look at number 2, among the subjects surveyed as part of a survey, several subjects are randomly selected and their heights are recorded. So we're measuring something. So if you think about when you measure it, you typically will measure it with some sort of yardstick or ruler or something like that. And there are infinitely many values along this ruler. So this is an idea of continuous data, the heights. Now, just as a side note, you do want to think about the tool we're using to measure this, and that's where it's giving us continuous. Technically, if you were stopping only at like maybe a feet of or an inch of precision, there's an argument to say that is discrete because you basically have to go ahead and say it's like they're 5'6" or 5'7", but the tool we're using implies that we're really considering it's maybe they're like 5 point, so if they were 5'6", 5.5, and maybe they had a little extra centimeter or two, like 5.51 inches, or this would be feet. So this is going to be considered continuous data. All right, now we have the 4 different levels of measurement. So remember that nominal and ordinal, these deal with categories, where ordinal, of course, our categories with order. So the example we used back in the notes is that the letter grades are an example of ordinal data because, again, you have the category of those who got A's, B's, C's, so on. And the A's, of course, are scoring higher, performing better than the B's, and so on. So those are categories with orders of ordinal. Nominal would be something that's just like a color classification, but there's no hierarchy. And then, of course, we have the interval and ratio. These are numerical in nature, but it all depends on if there's a natural zero. In the case of interval, so maybe off to the side, so there's, in the case of interval, this is where we have no natural zero. So this would be things like on a timeline, or in the case of ratio, these do have a natural zero. So you may want to think of something like a timer, for example, or e.g. a timer. So we go ahead and look at our 2 examples, our questions now. A American football historian recorded the years in which a team from the AFC won the Super Bowl. So this is, if we're just thinking about what this data looks like, this would be, I have no clue. I don't follow football that well, but like there would be like 1998, 2005, so on. This would be what the data looks like. And there's no natural zero. Even year 0 is just the idea of the transition from BC to AD. So there's no natural zero here, but it is numbers. So this is an example of interval data. Now, in the case of number 4, the color of M&Ms, and here we have the data as red, orange, yellow, brown, blue, green. These are randomly selected, but we're looking at the levels of measurement here. These are categories. If you were to go ahead and basically make little buckets, like if you were to make one bucket for the red, you would make a bucket for the orange, and so on, and then you were to place them in the corresponding bucket. Again, the idea is that there's no hierarchy here, so it is just going to be a nominal level of measurement. All right, so that completes 1-2. On 1-3, we learned about different sampling methods. So random, and just to maybe kind of remind you, but if we go back to the 1-2 notes and we look at the first or maybe second page, oh, this is 1-3. Let's go back to our 1-3 notes. We have our different sampling methods here. So the simple random one right here is just going to be, we're collecting data. Computer, typically to avoid human bias, you need to use some sort of software that has some random number generation to pick truly randomly without any bias. Systematic is where you select every case subject. So here we're looking at every third car. So here K is 3. Convenience sampling is just when data is easy to get. So you just maybe talk to whoever's closest. Stratified and cluster, these get a little bit confusing in terms of like making sure you select the right one in the scenario. Stratified deals more with characteristics. So you take all of the people that you're taking your population, and then you're grouping all of them under the same characteristic. So here, male and female, and then you're randomly selecting with the same amount within each of those different strata. So basically, you have an equal distribution of whatever the strata or characteristic is. Where cluster, typically more based on geographic location, but you partition the population into clusters, and then you randomly select all members of a selected cluster. So these are our 3 selected clusters, but again, we technically have another cluster if we were looking at just blocks. I think the notes did like an example of polling station. So you would go to a polling station and then ask everyone in that polling station. So let's go back to our review and see how these questions, which ones or what sampling method we're looking at. So number 5, we're looking at bird population densities, and they were studied by using this method, the line transect method. Don't need to know that for the case of this problem, but it might be something to look up if you're curious. And here they were flying an aircraft along the shoreline of Lake Huron and collecting sample data of intervals of every 20 kilometers. So here, this 20 kilometers, they're doing this in a systematic way. In the case of number 6, the statistician collects sample data by randomly selecting 5 books from each of the categories. So we're looking at categories here: science, literature, history. And then from each of them, you're selecting 5. So it's that same principle as before. You have all of your science books over here. You have all of, let's say there's 6 here. Then let's say we have 8 literature books. And then let's say we have 5 history books. So science, literature, history. Well, what you would do is that you would select randomly 5 from each of these. And we don't have much choice in history, but that is what we're looking at when we're looking at a stratified. So again, we're looking at the characteristic, and then inside each of the strata, we select the same number. 7's a little bit tricky. So let's go ahead and just erase that for now. In a clinical trial of the cholesterol drug Lipitor, subjects were partitioned into groups given a placebo or a dose of various sizes. The subjects were randomly assigned to different treatment groups. So your temptation here is to actually think about it as stratified or cluster. But we want to think about like what's happening here. If we were to partition these groups, the subjects were partitioned to different groups. So we have this 10 milligram group, the 20, the 40, the 80, and then we also have the placebo. So the P, the 10, the 20, the 40, the 80. So it's starting to feel like stratified, but we got to be careful. Are we selecting from that group? No, what happens is let's say we have subjects. Let's say we had maybe 10 of them. If we had 10 subjects, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We already have done this. This right here is our sample. And then what we're doing is we're placing those into different groups. So the sampling actually happened already. So what we're really looking at is where did these come from? They were randomly sampled beforehand. So we got to be careful. This does not fall into the stratified or the cluster, because it's not that we're not using those strategies to sample. We've already done the sampling, and now we're going to basically say, okay, this first one go here, second one could go here, third one could go here, fourth one could go here. But the sampling in this case was actually simple random. So that one's a little bit tricky. And I guess we're kind of implicitly saying that the sampling was done simply random, but it does not fit into the cluster or the systematic based off of the definition. So we go back to our simple random one. All right, let's go to the next page now. All right, in section 2-1, we were looking at a frequency distribution here, and we're asked to find the class width, class midpoint, and the number of data values represented in each of these frequency distributions. So if we were to look at the class width first, the class width you could think about is going from the one lower boundary to the next. So here we would have, and you can go from compare these lower boundaries, any of them. So you can easily see, let's just do the first two lower boundaries. 100 is the second class's lower boundary. 0 is the lower class's, or the first class's lower boundary. So our class width is 100. You can think about this as just simply as the number of values within a class, but be careful that 0 is included. So don't just subtract 99 minus 0, get 99, because that first value is the starting point of the class. Now, the class midpoints, on the other hand, are going to again, there's multiple ones here. This is plural. So our class midpoints, plural, well, is what is in the middle of two numbers. So if you were to look at the first one, 99, and then to find the midpoint, you would just have to go ahead and add the two numbers and then divide them by 2. You can think about this as your midpoint formula back from college algebra. So the first one is going to be 99 divided by 2, so it's going to be 49.5. So that is the midpoint of the first class. The second class would be 149.5, and then so on. And then the last one, let's write them like as a list. So let's just maybe back this up. So 49.5, then 149.5, and so on. And the last one is 649.5. And then lastly, the number of data values, well, you just add up all the frequencies. So if you did, so in this case, we typically represent it as n. N is equal to 1 plus 51 plus 90 plus 10 plus 0 plus 0 plus 1. You add all of that up, you end up with 153. A lot to unpack there. Again, I would recommend, if there's a problem that you're uncomfortable with, go to the additional practice problems and then work through some extra ones, just to make sure that you do one independently. All right, For number 9, we're looking at the relative frequency distribution as well as the cumulative frequency distribution for the frequency distribution given above. So we have to also use this up here. So let me fit those on the screen. That'll work. All right. So the relative frequency distribution is we basically are going to convert everything to a percentage. So relative frequency, these are going to be percentages. So you're going to just look at essentially the for each row, it'll just be the frequency divided by n. So in this first case, it's going to be 1 divided by 153. And let me just zoom in here for the time being. If you did that, you would end up with, let me go ahead and pull up a calculator. 1 divided by 153. So 0.0065. Now, careful, that right there is not the percent, that's the decimal. So if you multiply that by 100, you get 0.65%. So it's going to be equal to 0.65%. And then the second one, going back up to the top, let's go ahead and see what our n was, 51. So here, 51 divided by 153. So if you were to work that out, you'd end up with 33.33%. And the rest of the computations are similar. So the answers to the remaining ones are 58.82%, then 6.54%. And then looking at these last two, let's see, make sure I have those right. Yeah, so, and then 400, so this is going to be 0%. 0%. And I think there's actually a little bit of typo in the answer key. I think this last row is missing. Let me slide over and double check. It's also a good reminder to just point out, hey, the answers are at the end of this. So yeah, that last row is missing right here. So didn't quite box like I wanted it to. Let's try one more time. There we go. So this last class, 600 to 699, is also one out of there's just one in that class. So it would just match the same as the top. So going back over here now to the problem we were working on. All right, so that's going to be 0.65%. And again, you could always check your answer here by just adding up all of these, and these should add up to 100%. All right. Now looking at the cumulative frequency distribution, this is the cumulative. So to accumulate means to increase. So if you think about as you go down this column, that should be increasing. So the first one, well, it's going to match. So the first one's going to be 1. So just this first one carries over. The second row, though, is going to be what we had from above. So 1 plus the 51 new ones that we've encountered. So that's going to be 52. And then we have 90. So the next one's going to be zooming in now. It's going to be the 52 from right there, plus the 90 in the third row. So that's going to be 142. And again, you could continue down this pattern right here. Let's see, then we'd have 152, then we have 0. So again, 152, then 0, then 152, then 1, so 153. And the way that to check this one is realize that this last number should be our n. It should be whatever our frequency is. All right. Let's go to the next page. The next page, we're asked to name the distribution shape for each histogram. Remember, a histogram is just a visualization of the frequency distribution. But here we don't need to construct it. We just have to remember that something that goes low, high, then back to low, and does have some symmetry to it. This is a normal distribution. This one, this actually goes a little bit different order than I naturally do. So it goes down instead of across first. So this right here, these are all roughly the same height. So this is referred to as a uniform distribution. C, here we have some extra data on the right. So we have extra on the right. You want to think about how do these differ from normal. So this is skewed, and it is skewed to the right. Sometimes skewed to the right and skewed to the left are mixed up because you could kind of think about it like this one feels like it's heavier on the left because there's more data on the left, but it's the skew is where the extra data is. So therefore we would say D is skewed to the left. And that's the only problem on this page. We're now in chapter 3. So this is where it gets a little bit more computational, and you'll have to remember your measures of central tendency, your measures of variation. And as I go through this, I'll expand on the details as we need them. All right. So listed below are the number of Atlantic hurricanes that occurred each year. The data are listed in order by year, starting with 2000. We're asked to find the four measures of central tendency. All right. So the mean we think about as the average. And by the way, all of the formulas are provided. If you go a little bit at the end of this document, after the answers, you'll see the formula sheet as given on the test. So here we're looking at the sample mean, and you can see the sample standard deviation, z-scores. Now we don't have the formulas for mode or mid-range, so do keep those in mind. Those are not provided. Those are pretty simple. Mode is not even a formula, it's just an understanding of the data. All right, so listed below, already read that. So the mean denoted X bar. This is not all of the hurricanes. This is just the sample from these. Let's figure out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 years. So here n is equal to 14. So what we need to do is we have to add up all these numbers. So 8 plus 9 plus 8 plus, and I'm going to just do dots, and we've done this several times already through the semester. So if we were to add up all of those numbers and divide that by 14, that will give you your mean. And here, X bar is going to be 7.7. So the mean number of hurricanes each year is 7.7. The median is going to be the middle number. So the downside is to figure out the middle number, we do need to actually remember is the median. So let me just write this. So it's the middle number when sorted. So it's not just the middle number in the list, it's the middle number when sorted. So we have to sort this data first. So let me go ahead and just maybe sort it over here, zoom in. I should have done this ahead of time. Oh well. So 2 is the smallest. So I'm going to just cross that out. Then we have, let's see, 4. It's right there. Any 5s? We have a 5. We have a 6. We have 2 7s. We have 1, 2, 3 8s, 4 8s. 1, 2, 3, 4. We have a 9. We have a 12. And we have a 15. That was a tough year. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh boy, I missed one. Oh, we have 2 9s right here. So let's see how I checked that. Be careful. So let's slide that over, put a 9 here. So the middle number, you can just think about this like, okay, it's probably, to me, I'm a very visual person. So I'm like, okay, so it's not 2 or 15. It's not 4 and 12. It's not 5 and 9. It's not 6 and 9. It's not 7 and 8. It's not 7 and 8. Well, there's 2 middle numbers here, but they just happen to be the same. So do keep in mind that here is going to be 8. You basically take the mean of the middle numbers. So 8 plus 8. 16 divided by 2 is 8. So it's nice there because they were the same, but keep in mind that for the median. The mode is simply the most common number. So here the mode, the most common number was also 8. And then the mid-range is going to be the min plus the max divided by 2. So the smallest number is 2, the largest number is 15, divide that by 2, and then you end up with 8.8. Be careful here. We were not asked for the range. The range is the max minus the min, which of course is going to be 13. And 13 is not in the middle, so it really wouldn't be classified a measure of central tendency. That's a measure of variation. I think we have one of those down below. We don't, so. Anyway, just FYI. All right, 3.2, we were looking at sample data that has a standard deviation of approximately 4.56. So we don't need to compute the sample standard deviation. That takes a little bit of time because you have to essentially make that table, and then you have to, well, just to maybe call it out. Remember to do this, you have to make the table. You have to find the difference between each data value and the mean. Then you have to square each of these. Then you have to add them up. Then you have to divide by n-1. Then you have to take a square root. So quite a long procedure. And by the way, the fact that it's not on the review means I would not stress too much about it in terms of your preparation, but we are asked for the variance. Remember that the variance is s squared by definition. So here, the variance is going to be 4.56, and then you square it. If you type that into a calculator, it works out to approximately 20.79. And that's all there is to variance. All right. Section 3-3, this is where we were talking about measures of relative position. So basically, how does the data relate to each other? So suppose that the tallest man has a height of 247 centimeters, and the tallest woman is a little bit shorter at 236 centimeters. The heights of men have a mean of the 175 centimeters. So this is the mean, and we're not talking about a sample right here. So again, we talked about this later in the semester. We're technically claiming that that is the mean height of all men, and we now have ways to basically, with some level of confidence, say that. And a standard deviation sigma of 7 centimeters. Find the z-score corresponding to the height. So the z-score, and looking at our formulas right here, there's 2 of them. This one is when we're dealing with the sample. So here's our sample. This is our population. Again, just symbolic switches. So we're going to use technically the second one because we're not dealing with this sample per se. So it's going to be x minus mu divided by sigma. And remember that x is some data value you're given. So we're asked to find the z-score of the corresponding to the tallest man. So this right here is our x of 247 centimeters. And now, plugging this in, be careful that you put it in the right order. This one's above average, so we expect our value to be positive. Our z-score is either positive if it's above the mean or negative if it's below the mean. So plugging that in, we do kind of do a mental computation right here. If we were to do 247 minus 175, so 247 minus 175 is 72. Then we divide that by 7. So that's 10 point, oh, I already forgot. Anyway, I have it up on the screen. So this is going to be, well, let's go ahead and write it. So 72 divided by 7. 72, divide that by 7, and we get 10.29. Now that is way above average. So that's like in the 0.000001% of the tallest or percentile. So remember that when you're looking at z-scores, they're typically between -3 to 3. That counts for, according to the 50s. Well, let's just go back to the notes, and then we have the visualizations as well. The empirical rule, which says that 68% are within 1 standard deviation, 95 are within 2 standard deviations, and 99.7% are within 3 standard deviations. So like 10 is way over here. So if this curves continue way down, you're going to have barely any area left there. So keep in mind that, yes, this number is large, but it's talking about the tallest man. So, all right. There is 3-3. Oh, a little more on 3-3. So number 14. So 14, we are looking at the heights of women that are normally distributed. So we know they're normal and has a mean of 162 and a standard deviation. So we have a mu of 162, a standard deviation of 6 centimeters. And we're asked in part A to find the data values that would be considered significantly high. So these are all of those that are more than 2 standard deviations away. Oh, I think that's talking about it here. The data value considered significantly high if its z-score is greater than 2. So, I mean, you could go ahead and set up the formula, I think is how it explains it in the notes, but I found many students prefer just to be like, okay, I need to go ahead and look at 100. So this right here, let me do this in a different color. The mean has a z-score of 0. So to get significantly high, I have to take 162 and I have to add 2 standard deviations to it. So this, let's just put it in symbolic form. So this is mu plus 2 sigma. So 162 plus 2 times 6 gives us a 162 plus 12, or 174. So significantly high values are greater, and we're using greater than or equal to here, it's stated in the problem, greater than 174. All right, part B, same idea, except for is going to be looking at those that are significantly low. So same principle, you just do 162, well, so is mu. This time it's minus 2 sigma. So 162 minus 2 times 6 is going to be 162 minus 12. So that is 150. So significantly low values are those that are less than or equal to 150. So you could also, and I'm not going to write here just to go into, I don't want to get in the weeds and overcomplicate it, but essentially you can also do this by doing significantly low would be x is equal to the, minus 2, this should be a z-score. So minus 2 is equal to x minus the 162, the mean, divided by the sigma. Solve this, it gives you that same 150 for your x. Here we're looking at percentiles and quartiles, and percentiles, remember, are basically mapped to quartiles. The second quartile is the 50th percentile. So we're asked to find the percentile corresponding to this data value. So you can see that that data value X is right here. And let's figure out how many. Oh, N is 50. The unfortunate part is this isn't lined up very well. I think earlier in the notes, we had this in basically like a 10 by 5 grid or 5 by 10 grid, but you can see we have like 1, 2, 3, 4, anyway, not 10 values across the top. So if to find the percentile, we basically think about how far through the list have we gotten here. And we can look at our formula sheets. So we have a formula for the percentile of a data value. It's just going to be the numbers strictly less than the value time divided by the total number of data values times 100. So the number of values less, so we will have to count this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15, there's 15 in the first row, 30 by the time we get there, 31, 32, 33, 34, 35, 36, 37. So notice that there are 37 values less than the given X. So it's going to be 37 divided by 50 times 100. Type that into a calculator. 37 well, that one's pretty straightforward. It's going to be 60 plus 14, so 74%. So this is going to be the 74th percentile. And now we're moving on to chapter 4. In chapter 4, we learned about probability. So let's look at the problems we're going to encounter here. In number 16, Mark grabs a utensil out of the drawer without looking. The drawer has 7 knives, 9 spoons, and 6 forks. Mark is really living on the edge. So a little typo there, that shouldn't have been a question mark. So round your answers to 3 decimal places. We want to figure out what is the probability that he grabs a fork. So what we do need to figure out is, well, how many utensils are there in total? So 7, 9, and 6. So total, there is 7 plus 9 plus 6. So 15 plus, so 22. So there's 22 utensils in total. And the probability that he ends up grabbing a fork, well, there's 6 out of the 22. And now, let's see, 6 divided by 22 is 0.2727 continuing. So 0.2727, but we round that up to a 3. Yeah. All right. And remember, don't convert these to percents. Probability is a number between 0 and 1 inclusive. Now, what's the probability that he grabs a knife here? Well, it's going to be the 7 out of 22. And in the same computation, that's going to give us, I'll just check the answers, 31.8. So 0.318. So verify that you get the same thing. Now 17, again, it's another 2-parter. So it looks like here's part A on this page. Let A be the event that Mark grabs a fork, as in problem 27A. I think that should be 17A. Find the probability of A bar, or A complement. So remember that this is the denotion of the complement event, and the total probability is 1, so the complement is just the 1 minus the probability of A. So the probability of A bar, where A is the event that Mark grabs a fork, is 1 minus the probability of A. So that's 1 minus 0.273. And that works out to 0.727. So the complement event, you could check that by adding those two together, and you'll find that the sum of the A and A bar probabilities is equal to 1. All right, number 18, we're given this table. And this table right here is showing the probability space for the sum of two dice rolls. So you can see right here, 1 and 1, you roll two dice, you get a 2. 2 and 1 roll, you get a 3. 2 and 1, also 3. And again, you're rolling two dice at the same time. So you do have the two different scenarios, the like 1 and 2, and then you also have 2 and 1. So it's not sequential rolls, there's two dice being rolled at the same time. So there's a total of 36 possible sums. So if two fair dice are rolled, find the probability that the sum is going to be less than 4 or greater than 10. So the probability is the sum is going to be less than 4, or the sum is going to be greater than 10. Well, remember when you're dealing with or, and these are mutually, or we're asked if they're mutually exclusive events. So the sum is less than 4 and the sum is greater than 10. They are mutually exclusive because they can't both occur. A number can't both be less than 4 and greater than 10. If we said it was greater than 4, then these were not mutually exclusive. But since they are, we have just the probability of the sum is less than 4 plus the probability that the sum is greater than 10. And if you don't even worry about mutually exclusive, you would just then the formula, let me reference the formula right here. It is this one. The probability of A or B is the probability of A plus the probability of B minus the probability of their intersection. And this is another way you could say and. So going back here, so the sum is less than 4 and the sum is greater than 10. Well, in this case, realize that this is impossible. So that's going to have a probability of 0 here. So let's look at the first two. So the probability of the sum is less than 4, well, you could just 1, 2, 3. There are 3 different ways to get a sum less than 4. So that's going to be 3 out of 36 plus greater than 10 is 1, 2, 3. That's 3 out of 36. So you could also, if you compute these, you can just add the fractions, or you could go ahead and just convert them to decimals. So if you added the fractions, it would be 6 out of 36. And 6 divided by 36 is 0.167. Again, you could have also just do 3 divided by 36 and then add 3 divided by 36 independently. But there we go. In the case of number 19, these, well, maybe just a step back, are the events mutually exclusive or are they disjoint? Yes. And because they were a yes, we had this go to 0. In the case of 19, if two dice are rolled, find the probability that the sum is odd or greater than 6. Well, you can see right here, you can have an odd number greater than 6, 7, 9, or 11. So the answer to this is no, they are not mutually exclusive. So this third term is going to basically be non-zero. So we do have to consider that in our computation. So if we were to look at the scenario here, is the probability that the sum is odd or the sum is greater than 6, well, here, let's see what we can do. Well, we need to find the probability that the sum is odd. Add to that the probability that the sum is greater than 6, and then subtract essentially the scenario of the odd and greater than 6. Going back to the table, let's go ahead and just clean this up and start fresh. So if you look at the sum is odd, exactly half of these numbers, so if you just circling a couple of these, if you take a moment, reason through it, half of the numbers are 18 out of the 36 are when the sum is odd. And then the scenario, and let's go and just circle all of these, and maybe to emphasize, you can see right here, those 7s are also going to be circled when we do the sum is greater than 6. So if we do all of the odds, those will be all of these here circled in blue. But the sum is greater than 6 is going to basically be all of these that I'm putting in the triangle. So you can see there would be some that would be counted twice. And if you were to count all of the numbers that are greater than 6, we'll see that 21 of the 36. So if you added up 18 and 21, well, you're already over 36. So we do need to consider the subtraction of the odd numbers that are greater than 6. So that would be the ones that are circled in the red triangle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of 36 will be the number that fit that last statement. So maybe just realigning these. So that goes there. And this gives us our computation. Adding our fractions, we end up with 18 plus 21 minus 12 divided by 36. Common denominators, you can just add the numerators or add and subtract here. And then you'll end up with 27 out of 36. Converting it to a decimal is going to be 0.75 approximately. And again, the final is multiple choice, so reason through your answers. If your answers are all decimals, make sure that you appropriately convert it and just check that your answer makes sense. Now with 4-3, we are going to look at this following table with the data about drive-through and accurate orders. We are told that n is equal to 1,118, and you can verify that by basically adding up all of the different cells. So you can see there are 329 orders from McDonald's that are accurate. There are, in the same way, there are 13 inaccurate orders from Taco Bell. So if you added up all of these different cells in the table, you would end up with the 1,118. So that's just a little bit of a bypass of some computation if we read carefully. Now 20, if one order is selected, we find the probability of getting an order that is accurate given. So this is where we're going to be looking at conditional probability that the order is from Taco Bell. So our conditional probability formula is this one right here. And you can use the formula directly, or you can just reason through it. I think most reason through it fine. So if we're looking at this, given is where you start. So if we're given an order from Taco Bell, we're only going to be looking at these orders. So we're basically given 145 plus 13, or 158 Taco Bell orders. And then of those orders, we just are going to be looking at those that are accurate. So the accurate orders are 145. So here we have 145 out of the 158 orders. That's going to give us our desired probability. So 145 divided by 158 is 0.92 or 0.918. So approximately 0.918. As a side note, you could also, that's the most natural way I've seen students work with this one. The other way, probability of essentially accurate given Taco Bell, is to look at their intersection. So how many accurate orders are there from Taco Bell? So that is going to be, well, let's write it all. So the probability of accurate and Taco Bell And then it's going to be divided by the probability of just Taco Bell, just referring to this formula right here, where B is the event we're conditioning on. So you could kind of think of that bar as a fraction, if it's not, even though it's not. So in this case, we have the accurate order. So it's 145 divided by how many accurate orders from Taco Bell? 145 out of the total 1,118. Notice that's technically, that top probability is looking at just the full probability space, all of n. Then you divide that by Taco Bell, which is going to be 158 of the 1,118 orders. Multiply by the reciprocal. These cancel. You get the exact same fraction that we got over here. I prefer this way. It's a little more intuitive for the level of probability that we need. This formula is still good to know for advanced probability, but just reason through it like so. 21. If one order is selected, find the probability of given an order from McDonald's given that the order is not accurate. So this is the exact same procedure as above, just dealing with McDonald's instead of Taco Bell. So we're given that the order is not accurate. So we're going to be looking at all of the inaccurate orders. So that is our probability space here, is the one we've restricted to based off of what we're given. So we're given 33 plus 54 plus 31 plus 13. So that works out to 131 orders. And then we want to find the probability of getting one from McDonald's. So that's 33. So the answer is 33 out of 131. So that is going to be approximately 0.252. 22. This one is not using the table, so this problem is independent of the ones above. In the US, the true probability of a baby being a boy is a little bit higher than half, so 0.512. Among the next 4 randomly selected births, what's the probability of at least one of them as a girl? Don't think we have the probability of at least one here. No. So it's one of those you really have to reason through. So the probability of at least one is going to be 1 minus the probability of all are not. So this is kind of a generalization, but so let's see how we do this. So if we want at least one girl, this is going to be 1 minus the probability of all boys. And more specifically here, I'm going to replace this for all with 4 because that's what we were given here, the next 4 births. So this is 1 minus, well, remember, sequential events are multiplied. And again, the birth of one child does not affect the birth of the next. So it's just going to basically be 0.512 times 0.512 times 0.512 times 0.512. So simplifying that, that's just raised to the 4th power. Plug this all into a calculator, you end up with 0.931. And just think about this. 4 births, at least one of them needs to be a girl. This is going to be a fairly high probability, even though each one independently is the complement, so 49% roughly. Percentage chance or 0.49 probability. Do that over a couple different events. It works out to be a fairly high probability. Now in chapter 5, we learned about probability distributions. So again, not specifically asked here, but remember for the probability distributions, we have our random variable here, x. So that is our random variable, and it does need to be numeric. The probability of a certain, the probabilities of all of those being added up should be equal to 1. So when you add up the probabilities of each X occurring, you need that to be equal to 1. And of course, these all need to be proper probabilities. So the 4 fair coins are flipped. X is the number of tails among 4 coin flips. And by the way, we really should say like these are flipped sequentially because if you were to flip, well, I guess it doesn't matter. So I was thinking about the dice problem from earlier. But anyway, yeah, so we flip 4 coins. What is the number of tails among or X is the number of tails. So there is a 0.0625 probability of getting 0 tails. There is 0.25 or a 25% chance of getting just 1 tail, and then 4 or 3 heads. And then here there is a 0.375 probability of getting 2 tails and 2 heads, and so forth. And we really could list out the whole probability space here. It would just take a little while. So one possibility, the zeros, is essentially heads, 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 heads. Then the one head would be like, or one tail would be tail, head, head, head. Oh, too many. 4 coin flips. So let's back that up. Should just be 4. Sorry about that. Then there's also head, tail, head, head. Then there's head, head, tail, head, and so on. If you were to go through all of this and then, well, let's just do one more. Then the last one would be head, 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 tail. So there's 4. And if we kept going through this, we would be able to count how many different scenarios there are. Technically, I could count that really be 2 to the 4th or 16. So 4 out of the 16 of them are satisfy this random variable where there's 1 tail. So that's where this 0.25 is coming from, is again that 4 out of the 16. A little bit of a detour there, but hopefully that helps. Now, what is the random variable in the table and what are its possible values? So kind of answer this, well, the random variable here is just going to be the number of tails among 4 coin flips. And X could be 0, 1, 2, 3, or 4. This is a discrete random variable because, again, you can't have half a coin flip. So you're counting the number of tails. And does the table describe a probability distribution? Well, it does, and I already went through this because, again, these add to 1, X is numeric, and these are all proper probabilities. So, yes. And I'll just say C definition of probability distribution. All right, and part D asks us to find the expected value. So we do have the formula for an expected value right here. So this is the one we're going to use. And, well, it's a little bit of a computation. So it's going to be the sum of the, well, I'll just copy it exactly like we had here. So X times P of X. So X times P of X. So you take each row of the table, what this is saying, take each row, multiply these numbers together, and then you just add them all up. So it's going to be 0 times 0.625, plus 1 times 0.25, plus 2 times 0.375, plus 3 times 0.25, plus 4 times 0.6. 0.25. Remember to do your grouping appropriately. And then if you were to work all of this out, it is going to work out to be 2. And by the way, intuitively, that makes sense, because if you think about a fair coin, it has a 50% chance. So if you were just do one flip, there is a 50% chance or a 0.5 probability that it shows up as tails. So if you were to flip it 4 times, you expect 2 of them to be tails and 2 of them to be heads. So that's another way to interpret and intuit the expected value. Moving on to chapter 6, where we now look at probability with the things we did earlier in the semester, such as the sampling. We're going to start with the quick definition, or not even a definition as much as a concept. It's just remember that the total area under any density curve is equal to 1. So you can see that down here in the next one, that we have a uniform distribution right here, where x is the waiting time in minutes. If you think about this, if it's uniform, then basically there's a 10% chance you wait 1 minute, 10% chance you wait 2 minutes, and again, 10%, same as 0.1 probability. 10% chance is the same one as 0.1 probability. So you can see that's where we're getting our vertical scale here. Now, refer to this continuous uniform distribution depicted below and assume that a passenger is randomly selected. We want to find the probability that the wait time is less than 6 minutes. So again, there is a 0.1 probability that they wait 6 minutes, but there's also some probability that you have to consider where it's less. And that's all of this space to the left of it. We do not use the table here because, again, that table is for the normal distribution. This one is going to just be a matter of looking at the this in terms of a geometric figure. So if we look at this geometrically, we have a width of 6 and a height of 0.1. So the probability that the wait time is less than 6 minutes is going to just be the width times the height. So 6 times 0.1 or 0.6. Now we're going to possibly need the table. Read the question carefully to decide if that's true. A standard normal distribution is given, and find the area of the shaded region. The z-score separating the shaded region and the unshaded regions, z is equal to 0.28. So this is one of our z-scores. And then the upper z-score is right here. So we want to find the probability of selecting something from the sample where the z-scores are basically, or it has a z-score contained between negative 2.08 and we'll make that z. And again, whether it's less than or equal to isn't a big deal because it's continuous, but we'll go ahead and use the equal to match above. And we have 1.27 here. Now, we are given essentially some information. Let's start with this information right here. The probability of getting a z-score less than or equal to negative 2.8 is 0.0188. So that's actually this area right here. We don't want to put that as our answer because that's not the area of the shaded region. And again, where that comes from, if we look at our z-score table and we find negative 2.08, so negative 2.08, so that is right there. So that is where we're getting this value given to us. So we're also given, I'm not going to clutter the image, but this right here is giving us this along with this. It fills from the left to the right, so we have all of this area, red and gray. So what we really just need to do is a quick subtraction. We have, and I'm going to write it out. This line might be unnecessary if you have mastered this idea, but it's the probability that we get a z less than or equal to 1.27 minus the probability of getting a z-score less than or equal to negative 2.08. So working this out, we end up with 0.898, which was given to us up here, minus 0.188. And then when you work out the computation, that works out to 0.8792, 0.8792. By the way, if you were to get a negative number, probability has to be between 0 and 1 inclusive, so that means you flipped them. So just reason through it carefully. Number 27, we're asked to find the indicated z-score. So this time we're given the area of 0.1515, and we need to find that z-score. Remember that 0 is in the middle, so our answer should be negative. So the way we do this is we essentially have realized that this area is 0.1515, and that is from the left. So all I need to do is we have to go ahead and find this in the middle of the table. Find in middle of the table. So going back to our z-score table, we already know it's negative. So 0.1515, let's see, 0.1515 is right here. So that's going to be negative 1.03. So here we find that the z-score is 1.03, negative 1.03. And that makes sense based off of what we said. That should be left of 0. Now, in section 6.4, we learned about the central limit theorem, where we then had to consider what happens when you have a larger sample. You're not just picking one. So the fact that we have a sample of size 45, even if it weren't normally distributed, it would still work. But because it's normally distributed, we don't necessarily need the larger sample size, but still worth to note that. So if we are given a mean of 1,215 and a standard deviation of sigma equal to 411, let's go ahead and visualize what we're asked to do. And we need to find the probability that they have a mean less. So look at 45 SAT scores. They want to have a mean less than 1250. All right. So this is normally distributed. So if we visualize it with our curve, we know that that's not the best curve I've ever drawn. Let's try that again. So in the middle is the mean. So that's 1215. And again, this has not been standardized yet. So that's okay. We said 0 is in the middle above, but again, in standardized, when everything's standardized, the mean is 0 when it's converted to a z-score. So what we're going to need to do is do the conversion appropriately. And I don't think we have, let's see, let me check what formulas we're given. Oh yeah, so right here, we are given this one, the central limit theorem. So that is our z-score conversion under the central limit theorem, which is when we have a large sample size. So we do need to do x bar minus mu divided by sigma divided by the square root of n. So z is equal to the x bar, which we're looking to find their mean. So this is our x bar, minus the mu divided by sigma divided by the square root of n. So that is going to be 1250 minus 1215 divided by 411 divided by the square root of 45. So that is going to give us the z-score. So let's go ahead and I'm going to just pull this up here. So querying this. So we have to just careful with our computations. So if we do 1250 minus 1215 equal, that's our numerator. Then we're going to divide, but I'm going to open a parentheses and do 400. Oh, wait. 411, our standard. Is that our standard deviation? Move that over. Yeah, 411 divided by the 45, hit the square root, close my parentheses, hit equal, so 0.57. So close that. So 0.57. So that right there is my z-scores. So originally we have like our 1250 here, converting them to a z-score. This is 0, and now this is 0.57. So we essentially want to find this area. So going to our z-score table, we're going to find our positive 0.57 is right there. So 0.7157. So the probability that they have a mean less than 0, well, in this case, the 1250, of course, converting this to z-score, this would be 0.57 is 0.7157. For 29, we are in chapter 7 now. So this is confidence intervals. Take your time here. I remembered a lot of students struggled with this, but it is not an easy concept, but with some practice, you can do it. Suppose that a sample is used to estimate this population proportion P. So again, lowercase p here, we're talking about population proportion. The sample size, n, is equal to 600. So n is equal to 600. And of which 3% are successes. So p hat is equal to 0.03 or 3%. And we're looking at a confidence level of 98%. Calculate the confidence interval for the population proportion p. Going to our list of formulas, let's see what we're given. Well, we don't have the confidence interval for the proportion, but we do have the margin of error. Oh, well, yeah, so let's see, margin of error, here it is. The margin of error for the proportion. So remember that the confidence interval is basically just going to be the p hat minus the error is less than p hat plus the error. So let's go ahead and work this out. Remember that q hat is just 1 minus p hat. So, and we also need that z sub alpha over 2. So that z sub alpha over 2 is going to come from our confidence level. So let's go ahead and get our z sub alpha over 2. Well, if we have a 98% confidence level, let's just kind of reason through this. If you've done it a couple of times, you probably can naturally go through this. That means that 98% is in the middle. So in each side, the alpha over 2, we have 1%. And this is, so zooming in here, this vertical bar is negative z sub alpha over 2. So if I basically just find 0.01 in the table, that's going to give me this area. And then that will give me the negative of the z sub alpha over 2. So 0.01, let's see. So 0.01, the closest we get is right here. So it's really like 0.01's right there. But we'll just go ahead and do negative 2.33. So that's negative 2.33. The positive z sub alpha over 2 is positive 2.33. So 2.33. So now let's go ahead and use this to find the error. So the error is 2.33 times the square root of p hat, going back just to reference the formula, make sure I get it right. Yeah, the square root of p hat times q hat divided by n. So p hat 0.03 times q hat 0.97, which again is just 1 minus 0.03. That's my q hat. And then we'll divide that by n. So n is 600. Grab my calculator here. Let's see what we got. 0.03 times 0.97. That's the numerator inside. Divide that by 600. Hit the square root button and multiply by 2.33. I end up with an error of 0.0162. I don't think it's specified. No, it didn't specify precision. So then the confidence interval is just, like I said, the confidence interval is just going to be the 0.03 p hat minus the arrow 0.0162 is less than p, which we're trying to estimate with some confidence. And then we would have 0.03 plus 0.0162. So then we end up with working this out. Oh, the answer key did it to 3 decimal places. So this is 0. So just there. So this works out to 0.014 is less than p, is less than 0.046. Again, this is maybe the hardest concept from the semester. So spend some time with it to make sure you're comfortable with confidence intervals. That one was for the proportion. In 7.2, we looked at it for the mean. Yeah. So similar idea, except for we'll be using a different table, the t table, and we actually have that t sub alpha over 2 already given to us. So going back to our formulas, this one is just going to be, we need to find the margin of error when sigma is unknown. So the error is t sub alpha over 2 is the t-score. So the horizontal axis of the t distribution. And then S here is the sample standard deviation, and n is, of course, the sample size. So that's all given to us. Here, the sample mean, the sample standard deviation, and the t-score. So we have to find the margin of error, which is 2.403, and multiply that by the sample standard deviation, 12.1, divided by the square root of 50. So let's pull this up again. So I'm going to do 12.1 divide by, and again, just to make sure I'm okay, I'm going to do open parentheses 50 square root close parentheses, hit equal. So that takes care of this part. And now I multiply that by 2.403. And I have my margin of error of 4.11. And again, these are not going to be between 0 and 1 because proportions are between 0 and 1, just percentage of the total. But this one needs to essentially be wrapped around the mean. So our confidence interval here is x bar minus the error is less than mu is less than x bar plus the error. So 45.6 minus 4.11 is less than mu. And that mu is just a placeholder. Again, we're estimating or building a confidence interval to infer the population mean. So x bar again is 45.6 plus 4.11. Doing that computation, the workbook, I think, puts it in a interval notation. So it's going to be 41.488. They just do interval notation, but I'm going to just use this inequality, compound inequality again. So then the right bound is 49.712. So there is our confidence interval. All right, 7.3. This one, we are looking to find the chi-squared values given this confidence level and the sample size. So it's just really saying, okay, how do you work with this chi-squared table? Again, a chi-squared distribution is not symmetric. If we were to kind of graph this one, it actually starts at 0 and it goes up, and these chi-squared distributions are skewed to the right. So the degree of freedom, remember the degree of freedom is 1 less than n. So that's going to be 46 minus 1, or 45. And we have a 98% confidence level. So let's see, 46 or 45, well, this is kind of a tough one, so because it's right in the middle. So we'll just go ahead and I'll go back. We'll go ahead and work with 50 just to be safe. And let me just eyeball this really quick. Yeah, they rounded it naturally. So if we're dealing with a 98% confidence, so that means that we have 1% on the side, each side, 98% in the middle, and, well, the area to the right of the critical value. So that's 1%. And remember, if we'll need this, so this right here is the left chi-squared value, and this is the right chi-squared value. We have symmetry. So 0.99, reflecting it over this middle line, gives us the two chi-squared values. So 0.29707 and 76.54 are the two chi-squared values. So chi-squared on the left is going to be the 29.707, and chi-squared on the right is 76.154. In 32, we will now go ahead and construct a confidence interval using this chi-squared distribution. So, a set of 25 data values is collected in an insomnia study. The set has a mean wake time of 98.6 minutes and a standard deviation of 41.7 minutes. Assume that the sample values are from a normally distributed population and construct a 99% confidence interval estimate of the standard deviation of wake times for a population with the same drug treatment. So if we go to our formula sheet, let's go ahead and look over those. We'll see that for the confidence interval for standard deviation is a little bit different than the mean and the proportion, because we get the confidence interval directly instead of actually having to work with the error. So you can see right here, the confidence interval is just going to be, the lower bound is going to use the right chi-squared value, and the upper bound will use the left chi-squared value along with some other data or statistics already given to us. All right, so let's go ahead and see what we have. So a set of n equal to 25 data values. And we also are going to need S. So here we don't need the mean, but we do need the standard deviation. So S is equal to 41.7 minutes. And we have a 99% confidence interval. So this confidence level. So our confidence level is 99%. So this is what we're going to need to use to get our chi-squared values. So going to our chi-squared table, we have to not deal with 01 and 99 this time. We have to consider the idea that if 99% is in the middle, that leaves 0.05%. 0.5%. Or 0.005. in each tail as the area to the right. So that means we'll use this rightmost column and this leftmost column. So this is giving us my right chi-squared value, and this one is giving me my left chi-squared value. Our degree of freedom was 1 less than 25, so it's going to be 24. So here are the two values, 9.886. So the left chi-squared is 9.886, and the right chi-squared value is 45.559. So 45.559. All right. So now the confidence interval is just going to be the square root of the, just to make sure I don't mess it up in this recording, n minus 1 times s squared. So it's going to be, we'll just do the n minus 1. So 24 times 41.7 squared divided by the, again, it's weird because this is the left or lower bound, but we're still going to use the right chi-squared value. So, and again, that's just because we need a smaller number on the left, so we need to use the larger denominator. So 45.559 is less than sigma, because we're, again, is for the standard deviation, not variance. And the square root of 24 times 41.7 squared divided by the 9.886. So that's our setup. And I'll go ahead and do one of the computations, then I'll just refer to the solution manual for the other. Let's do the left one. So the way I would start this one is start with the numerator and square it. So 41.7, square that, multiply it by 24, divide it by the chi-squared value, so 45.559 hit equal, and now take the square root. So that is going to give me 30.27. 30.27. That's less than sigma, which is less than, and again, I'm just referencing the solution manual on a separate screen. So that is going to be 64.97 for the right bound. Now, on to chapter 8. So in chapter 8, we're working with hypothesis testing. So what is assumed to be true in every null hypothesis? That is to say that H naught is true. The null hypothesis is assumed to be true. And again, this is the notation that we use for null hypothesis, H sub 0 or H naught. 34. Given this claim, the mean pulse rate of adults is equal to 69 beats per minute. We need to write the null, an alternative, in its symbolic form. So our claim, we're using mu for mean, and is going to be equal to 69. Now, our null hypothesis always uses equal, so that means our null is going to be mu is equal to 69. And then because this is using equal, our alternative is simply going to be not equal. It's a two-tailed test. Do keep in mind the various other statistics in play. When you're dealing with mean, you use mu. Sigma is for your standard deviation. We also have p, and that's p for proportion. We make claims about the parameter. Again, the parameter just is about the population. So we also have sigma squared. I should have done that one earlier. That's for variance. And we have rho. And again, I saw a lot of mistakes happening on the test. P is different than rho. This is the Greek R, and that is for the correlation. So these are the different parameters we make claims about. On to 35. decide what type of hypothesis tests you would use for the claim p is greater than 0.9. Well, this is a greater than symbol, so we're going to be looking at a right-tailed test. So in the case of 36, again, we're using equality, so and the technically not equal to here. So still, even though it's not equal and not equal, it's still going to be two-tailed. In 37 and 38, we're going to be looking for the range of p-values for a given test statistic. So again, notice that this is a t-score, not a z-score. So n is equal to 24, so the degree of freedom is one less, is 36, or excuse me, 20, I don't know where I got 36, 23. A left-tailed test, so when we're looking at our distribution, we're going to be considering, let's try that again. We're going to be considering the left tail. And this is just one-tailed, so what we're going to need to do is use the t-score or t-table. So that is this one with the critical t-values. It's a one-tailed test. So just the left tail. And the degree of freedom was 23. Now we have a t-score of negative 1.852. So notice that as we look at our t-scores, these get smaller as we go from left to right. And this is the area in the right tail. So you can see right here. So if you just drop the negative, we won't have, well, let's back up. We are not given the area. We're given a t-score. So what we could go ahead and consider is just dropping the negative because we have symmetry. So negative 1.8 and some change, it basically puts us in this column, which is between these two. And since we don't have a specific column for negative 1.852, so 852, all I know is that the p-values fall somewhere in here. So this is what it means when we're talking about a range of p-values. It's not quite fitting, so I'll just do p-val. All right, so this is 0.025 is less than the p-value is less than 0.05. So the range is 0.025 is less than the p-value, which is less than 0.05. Similar process here, except for with a two-tailed test and the degree of freedom of 30 and a t-score of 1.275, we're going to need to use the area in two tails. So our degree of freedom is 30. So degree of freedom is 30. And positive, again, doesn't matter because of symmetry, 1.275 puts us right here. Nope, puts us over here. So we're at the right, we're right of the rightmost value. So all we know is that the p-value exists over here. So the p-value is going to be larger, or 0.2 is going to be smaller than the p-value. So here we'll say 0.20 is less than the p-value, or you can reverse it if you want, but that more matches the direction of the table. In 39, we're asked to match the values of the linear correlation coefficient R with the 5 scatter plots. Remember, the closer it is to a straight line, the closer it'll be to 1. And again, this one's decreasing, so we're looking at -1 here. This one has a little bit of spread, so a little bit to the left and right, but there's kind of the rough estimate of the regression line. It's positive, so it's going to be 0.992. This one is really far spread, but it does have this positive slope, so it's going to be 0.268. This one, pretty much a straight line, just in a positive direction this time, so it's going to have a R of 1. And now that I look at my other options right here, this one feels really spread out. Like it even took me a sec to figure out what direction this is. So technically, if I look at my remaining two options, so that's out, that's out, that's out. This one's closer to 1. So that one feels like it should go with B. So this one should at the point 0.26 should go with the C, and then this 0.746 is going to go with B. And then finally, section 10-2, we look at 40. Oh, wait, we only have, I thought we had just one more. We have two more. So 40 different hotels on the Las Vegas Boulevard, referred to as the Strip in Las Vegas, are randomly selected, and their ratings and prices were obtained from Travel City. Using technology with X representing the ratings and Y representing the price, we find the regression equation has this slope. So this right here is going to be the slope of the equation and a y-intercept of negative 368. We have I believe we have the regression line given to us, this formula I should say. Yeah, right here. So notice that B1 is the slope and B sub 0 is the y-intercept. The slope is always by the value of x. So let's go ahead and plug this into our regression equation. So y hat is equal to minus 368 plus 130x. Well, y hat by definition is a prediction, and here y's refer to the price. So it's the predicted price for a given rating. So y hat is the predicted price, because y's are dealing with the price for a given price, because x represents the price. Oh, excuse me, for a given rating. X is representing a rating. All right. Since we now have an equation to predict, we can just take some value of x. In this case, the rating is 3.5. And we can find y hat is equal to minus 368 plus 130 times 3.5. Plug that into a calculator and work through it. And we'll find that y hat here is equal to 87. And this is dollars. So if it's a 3.5 rated hotel, we can predict that the price is going to be $87. In 41, same principle, except for we did not have to go through the logistics to set up the equation ourselves. We're given this for y hat. And let's see what we have. We're asked to find the predicted weight for an adult male who is 180 centimeters tall. Now, we technically should probably consider if the height and weights of adult males are linearly correlated. If they weren't linearly correlated, then we should just use the y bar, or the average weight of adult. But here we're assuming, and if you look around, we do know that height and weight are correlated just empirically from what we observe. So we can use y hat. So if you plug in the given value, the predicted weight is x is equal to 180. We would find, well, we can type this last one in. So 1.10 times 180, and we have to go ahead and subtract 106, and we find 92. So y hat is equal to 92 kilograms. And that completes the review for Math 2023's final exam. Study hard, make sure you practice, get plenty of rest, and we'll see you at the final.